Hello and welcome to this video which is all about electromagnetic waves. Electromagnetic waves is a hugely important topic. They impact upon almost every area of our everyday lives. Here we're going to be talking about the whole spectrum from radio waves through microwaves, infrared, into the visible, which enables us to sort of see things and give us our everyday vision, down into the ultraviolet, the X-rays and finally the high energy gamma rays. Let's have a closer look at exactly what these waves are, how they're made and how they're detected. Electromagnetic waves are different to other waves in that there is no actual material which is doing the oscillating or waving up and down. Instead, in an electromagnetic wave, it's the strength of electric and magnetic fields which is changing in strength in a wave-like manner. Imagine you had a single electric charge. It's already got its own electric field. You could imagine the field lines radiating away from it. If that charge now accelerates or oscillates, then it will wave its electric field with it. That electric field will create magnetic fields and so on, setting up an electromagnetic wave moving away from the original charge. Let's have a look at a model that might help us to visualise exactly what's going on here. In this model, my yellow ball represents one of the electric charges in this metal rod, and the rope represents one of its electric field lines coming away from the charge. If I accelerate the ball up and down the rod, it shakes the rope and we can see how we have the wave moving away from the electric charge. This simple model shows how any accelerating charge will produce electromagnetic waves. It could, for example, be radio waves coming from a transmitting antenna. In there, an amplifier accelerates the electrons up and down the antenna, and as they do so, we get the electromagnetic waves radiated off. Alternatively, it could be the electric charges which make up any object whose temperature is above absolute zero. In those objects, the atoms made up of charges are oscillating because of their thermal energy, and so they too will give off electromagnetic waves. Of course, the story is only complete if we also think about how electromagnetic waves are detected. When those electromagnetic waves pass over other materials, the force fields can grab a hold of the charges in the object and oscillate them, shake them about, so that those charges are also moving in exactly the same way as the charges were in the object that produced the waves in the first place. We can use our ball and rod model to explain this as well. This time, if I make the waves while Eleanor holds the rod and ball, and I send the waves in, when the waves reach the ball, they shake the ball up and down the rod in exactly the same way that electromagnetic waves would shake the electrons up and down the aerial. This simulation from PhET shows the effect quite nicely. First, it shows the electron in the transmitter oscillating up and down, and it represents the radio waves coming away from that antenna. When they pass over the aerial on the roof of the house, they grab a hold of the electrons in that aerial and shake those, so they are then moving in exactly the same way that the electrons were in the original transmitter. In that way, we've both transferred energy from the antenna to the aerial on the roof, and we've also transferred the signal because the electrons are going to be moving in exactly the same way as they were in the original antenna. I've already mentioned that electromagnetic waves are unusual because there isn't any actual material which is doing the oscillating. This explains, in part, why it is that electromagnetic waves can travel through a vacuum. When, for example, waves are travelling through space, they travel at a speed of about 300 million metres per second. At that speed, it takes just about 8 minutes for the light to get from the sun to the Earth. So, as we've seen, radio waves can be made by oscillating charges in an antenna which can be detected when they pass over an aerial. And this doesn't just apply to traditional radio. As the wavelengths get shorter and we head towards and into the microwave region, it will apply to modern technologies as well, things like Wi-Fi, Bluetooth and mobile phones. Continuing into the microwave region, of course, we have our everyday microwave ovens, where the waves are of a particular wavelength and have the ability to grab a hold and shake the bonds in water molecules, meaning that anything that we put into the oven with moisture will end up getting its atoms moving faster, and therefore the object is hotter. Of course, all materials are made up of atoms, which are made up of charges. So in any object, the charges in the atoms will be oscillating because of the thermal energy. So all materials will be radiating electromagnetic waves. This simulation from PhET will enable us to explore how the wavelength of that radiation changes for objects at different temperatures. If we start off with the thermometer on the right, which tells us the temperature of the object, set at 300 Kelvin, which is about the sort of everyday temperature we would get on the Earth. The graph shows us the spectrum of wavelengths that we would get from an object at that temperature. The vertical axis shows us the intensity of each radiation, and the horizontal axis shows us the wavelength. There is a visible spectrum marked on the graph to give you an idea of how that wavelength compares with that of visible light. You can see that at these temperatures, all the wavelengths given off are much longer than that of visible light. We say this is the infrared part of the spectrum.
When I hold my hand in front of this hot cup of coffee, exactly the same thing is happening as we saw with the radio waves. The atoms in the cup are hot and they're vibrating quickly and emitting infrared radiation. This radiation travels out to my hand and starts the atoms in my hand vibrating, and that makes my hand feel warm. So we say that energy is being transferred from the cup to my hand. We can use an infrared camera like this to detect this radiation. It works like an ordinary camera, but is sensitive to infrared rays rather than visible light. You may have seen them on TV in police programmes where they track people using the infrared radiation coming from their bodies. They're also really useful in disaster situations, looking for survivors in earthquakes, for example. Additionally, they can be used for thermally imaging buildings, to test how good the insulation is and looking for hot and cold spots in the fabric of the buildings.
Let's see what happens if we increase the temperature of our object. As the temperature goes up, the intensity of the radiation, not surprisingly, gets greater, and very soon we have to change the scale on our graph. But as well as the intensity of the radiation increasing, something else quite important is happening here as well. If you look at the peak of the graph, that's the wavelength which is most intense, you can see that as the temperature goes up, that wavelength, that most intense wavelength, gets shorter and shorter. Does this mean that at some temperature our objects will actually start to give off light?
In this demonstration, I'm heating up a metal screwdriver in a gas flame. It starts off at room temperature, but as I heat it up, it starts to radiate at shorter and shorter wavelengths and higher frequencies. Eventually, it starts to emit wavelengths that we can see. The first wavelengths that we can see are in the red part of the spectrum. Hence, we can see it glowing red.
You can see this effect in the simulation. If we increase the temperature to that of the glowing screwdriver, you can see that the radiation begins to creep into the visible part of the spectrum. Now, if we increase the temperature further to that of the sun, you can see that the whole spectrum is now centred on the visible part of the spectrum. There are many different ways in which we can produce or generate light, but analysing the spectrum from hot objects like this can tell us an awful lot about the nature of that object. For example, we can tell the temperature of stars just by looking at their spectrum and relating it to these curves that we see here in the simulation. The visible part of the spectrum is in fact a very, very narrow range of wavelengths. And of course it is important to us as humans because those are the range of wavelengths that our eyes are responsive to, and so it gives us the whole concept of light and our vision. Because we've learned how to control light, we can develop instruments like telescopes and microscopes and cameras and of course spectacles. If we continue to increase the temperature of our object further, the radiation begins to creep down to even smaller wavelengths than visible light. We're now into the ultraviolet region. Now there are different ways of producing ultraviolet as well as from very hot objects. And ultraviolet is quite interesting because it produces some quite strange and interesting effects.
Some objects show fluorescence. To see this properly, we need to turn the lights off. So fluorescent objects will absorb radiation in the ultraviolet part of the spectrum that we can't see and emit it in the visible range that we can see. An example is this uranium glass here. Also, highlighter pens. Soap powder manufacturers often add brightening agents to their soap powder. These fluoresce, so when you see your freshly laundered clothes in sunlight, they appear to glow, making them look extra clean. A security feature of modern banknotes is to have part of the note that fluoresces while the rest doesn't. So by putting the note underneath a UV light, you can quickly and easily check for forgeries.
A word of caution here now. As we move down the spectrum to shorter wavelengths and higher frequencies, the energy of the waves is going up. And by the time we're in ultraviolet, the waves can have harmful effects. Ultraviolet is what is responsible for giving us a suntan. And whilst we often try and achieve that, I think it's desirable, it does have some serious health consequences. So the advice is always to try and stay out of the sun as much as possible. And if that's not possible, to protect yourself with sunblock. It can have positive advantages as well. There are, for example, garden pond filters which use high energy dangerous ultraviolet to kill off the organisms in the pond water which would otherwise make the pond cloudy or slimy. If we fire a beam of high-speed electrons at a metal target, which will cause them to slow down, stop very rapidly, then that rapid deceleration will cause the electrons to give off X-rays, very, very short wavelength electromagnetic waves. The ability of these waves to pass through the soft tissue of our bodies, but not through denser bones, means we can take X-ray photographs to show broken or damaged bones. Absolutely vital in a lot of medical diagnosis. Now, X-ray machines have been around in hospitals for a very long time and are quite commonplace, but the technology is now advanced and has given rise to such things as 3D body scanners, CT scanning and so on. Gamma rays emerge from within the nucleus, and they are the result usually of radioactive decay when protons and neutrons rearrange themselves within the nucleus. The loss of energy from the nucleus appears as an electromagnetic gamma wave. Now these are at the very high frequency end of the spectrum and are the most harmful. So gamma waves can cause significant harm to body cells, turning them cancerous. All of that said, they do have practical applications. For example, in sterilising single-use medical supplies. The syringes, bandages, dressings and other surgical instruments can be put into packets and sealed and put in boxes. The boxes are then exposed to intense gamma radiation, and the gamma waves will pass through the boxes, through the packets, and kill off any bacteria which are inside the packet with the instruments and the bandages. In that way, the package remains sterile until it is opened. On these dressings here, you can see that they've been labelled sterile with a letter R after them, the R indicating that they've been sterilised by exposing them to gamma radiation. So there we are. I hope that's helped to remove some of the mystery behind electromagnetic waves.